Okay, suppose we have a anti-click of, basically, if we have one node, we cannot have, we have anti-click of one, click of one, it does not satisfy it. If we have two nodes, we can have anti-click of one, anti-click of two, click of one, or we could have anti-click of one and a click of two. Those are the only two options. So this one satisfies it, but this one doesn't. So it's possible to construct a situation where it doesn't work, so that means that that number is too small. If we go up to 3, then we can have anti-click of, let's say, anti-click of 3, click of 1. If 3 is the anti-click and each one of those is a click, we can have anti-click of 2. So anti-click would be this one, anti-click would be that one, and click of 2. Or we can have anti-click of 2, click of 3. That's possible. Anti-click of 2, click of, well, no, this is just anti-click of 2, click of 2 still. Or we can have a click of 3 and an anti-click of 1. Those are the only options. So all of these are okay. All of those satisfy that, so we have ourselves the minimum number. So in this case, r of 2, 3 equals 3. And in fact, r of 2, any number n, equals that number n. So let's just go ahead and skip past that. So now we understand what a Ramsey number is. So now let's get to the good part. Basically, all you got to do is remember that every vertex is part of a click and an anti-click. Every vertex is by definition, because it's at least a member of a click of 1 and an anti-click of 1. At least that. So that's number 1. Number 2, if we take any vertex, we take any particular vertex, it is either A, connected to over half the other nodes, vertices, right? It's either connected to over half of them, or it's not. It's connected to less than or equal to half of them. So if it's connected to over half of them, then what we're going to do is we're going to create two lists. We'll have a list A and a list C. This would be an anti-click, and this would be a click. The anti-click list and the click list. And so we'll take this. If it's connected to over half of them, then we will take any arbitrary vertex. We take any vertex and we'll add it to list C. List 2, list 1, whatever you want to call it, the click list. We're going to add it to that list, and we'll discard all nodes, vertices, whatever. I'll use the word vertices. Not connected to this vertex V. We'll call this vertex V. So if we were to just pick any old random vertex out of there, if it's connected to more than half of them, we'll put that in the click list, and then we'll get rid of the ones it's not connected to. So we're trying to find the biggest click. If it's connected, or at least a big click. If it's connected, if it's not connected to over half, we do the opposite. We add to list A, the anti-click list, and we discard all of the vertices connected to V. We discard the ones that are connected because we don't want the ones that are in a click, we want the ones that are an anti-click. So in this case, let's suppose V was in a click, we put V over here, and we discard all the other ones that are not connected to it. If it does not have more than half of the vertexes connected, then we put it over here, and we would disconnect all the ones that are connected to it. So what that's going to do is, at each step, and I'll put this here, at each step, you discard less than half of the remaining nodes. So that goes back to that discussion we were having about log base 2. We're discarding at most half. I mean, no more than half. So so if we go through this process step by step, then what's going to happen is we'll have at the very most log n steps. Actually, it's 1/2 log n steps because we have two lists. And since one of those two lists is going to have at least 1/2 log n entries, I mean, in a perfectly balanced situation, each one might have 1/2 log n, but if there's even one difference, it would be skewed one way or the other, and we'd have at least one of them would have more than 1/2 log n. So let's take a look at an example. Take a look at an example. We'll create this graph. And we'll have it like this, say. And we will keep track of the vertex, the degree, the amount remaining, and whether it's in the click list or the anti-click list, and then the discards. So let's take a look at what happens. Let's pick node 1. If we pick node 1, then we're going to add it to whichever list. Well, what's the degree of 1? The degree is 2. How many nodes are remaining? 1, 2, 3, 4. So there's 4 remaining. Half of remaining is 2. Now the problem said put this one in the click list if it's greater than the number of remaining nodes. So 2 is not greater than 2, so it's going to be in the anti-click list. Node 1 is. And so we're going to discard the ones that are not, we're going to discard the ones that are connected to it, because it's in the anti-click list. So this one's connected to 1, and this one's connected to 1. So 2 and 5 are gone. Now if we take the next nodes, take 3. If we take 3, then we're going to that's going to be of degree 1, because we don't count these other ones. So it's going to be degree 1. And the remaining, there's only one remaining node, so it's 1/2 of 1 is 1. Sorry, 1 is 1/2. So is it greater than the number of remaining nodes? Yes, it's greater than that. So that means node 3 is going to be in the click list. So that one's gone. Now we discard all the nodes that are not connected to 3, but 4 is connected to 3. So that's the one. 5's already been discarded. So now we're going to take node 4, it's the last one left. Its degree is 0. And so 1/2 of 0 is 0. 0 is not greater than 0, strictly greater than. So C is going to be added to the anti-click list. Sorry. So node 4 is going to be added to the anti-click list, and there's nothing left to discard. So now we have a click list that has 1 of them in it, and we have an anti-click list that has 2 of them in it. Well, the number of nodes, n equals 5, so 1/2 log 2 of n equals 1.16. I calculated it out, you can check it out. But that's basically, we have to round up, so that's going to be 2. And we can see that 2, the anti-click list, is in fact less than or equal to 1/2 log 2n. Now, this did not give us the largest click, right? Because we have a click of 3 staring us right in the face. The purpose of this is not to prove to get the best click. All we're trying to show is whatever happens, no matter which of these nodes you pick, you're going to get either a click or an anti-click with at least 1/2 log 2n nodes selected in it. So, in one or the other of those lists. So I hope that helps you understand the material. Question 13, well, I hope that helps.